Okay, so recording. Hello, everyone. This is chapter 6, gases in our Chem 65 class. The approximate contents of this talk will be looking at kinetic molecular theory, or KMT, pressure, gas laws, the ideal gas law, and we'll say a few words about Dalton's partial pressure. All right, so without further ado, okay, kinetic molecular theory. If you look at the title, kinetic molecular theory, it's basically, theory means based on experiments. So people do experiments. Molecular is molecule. So people do experiments on molecules. Kinetic here means kinetic energy. So kinetic energy is the energy of motion. So this theory relates to gases. So really, it's just the theory based on experiment about how gas molecules move. You can answer the kinetic molecular theory in one word. The answer is diffusion. So gas molecules diffuse. This means that they move in straight lines. If the temperature is above absolute 0 Kelvin, they move nonstop. So molecules only stop moving at 0 Kelvin. So they move in straight lines, they move nonstop. They bounce without losing energy, so they undergo elastic collisions. Elastic collisions are not something that's very easy to imagine because at the macroscopic level, we live in a world with inelastic collisions. So for example, if you're bouncing a basketball, you have to apply a steady amount of force every bounce, otherwise the ball will just slowly rest on the floor. So basketballs undergo inelastic collisions. They lose energy. If a basketball were a true gas molecule and you let it go, it would just bounce forever to the same height. It wouldn't need to be pushed. So that looks weird. The visual looks weird, but it makes all the sense in the world because if you drove to wherever you are right now, or if you're at home and you've driven somewhere in a car today, you know that the air in your car tire was undergoing elastic collisions, because if it wasn't, it would condense to a liquid and there'd be no such thing as pressure. So literally, for the idea of gas pressure to exist, elastic collisions are obvious, they're necessary. Okay. So gases move according to kinetic molecular theory, and we assume that gases are point particles and the nature of the gas is irrelevant. We assume that gas molecules never get close enough to each other that they notice each other. So they're just specks of point particles moving incessantly, randomly, haphazardly, and they never stop. Okay. These equations down here, they're just to remind us about kinetic energy, seeing as that's what we're talking about, the energy of gas particles. So the equation on the left is just kinetic energy. It's in a slightly odd form, but odd can be cool too. It's a half mv squared. So here we've got U. I don't know why we've got U, but we've got U. So the kinetic energy is a half mv squared, where half is just the number of half. M is the mass of the gas molecule. V squared or U squared here is just the velocity squared of the molecule. This equation on the right, to be honest, is not that important for our discussion right now. It's nice in that it links in Avogadro's number, but essentially, you could, maybe if I can write over this, it's more relevant to a physics discussion, which I know this is not. I didn't want to take it out though, because it's kind of nice too. Let's see, I'm going to try and write on the slide. All right. So, I can't write on a red slide with a red pen. All right. So another way, what's that? Hang on. Sorry, I'm having technical difficulties. Let's see, I need something smaller. All right, is that going to work? Yes, all right. So we could write kinetic energy or EK or K, doesn't matter, kinetic energy. 3/2 KT. So this is, if this looks more familiar, this is another common way to write kinetic energy. So either kinetic energy is mv²/2, which is this thing over here, or 3/2 KT. So it's a half multiple of KT. How you get this equation over to this equation, you just use the fact that NA, or Avogadro's number, is the ratio of R/K. So Avogadro's number is the ratio of two constants. It's the ideal gas constant R that we'll see in these slides, divided by Boltzmann's constant K. If we substitute, if we solve for K and then shove it in here, we get the R/NA. So anyway, bottom line, these are equations for kinetic energy. All right. Okay, so on to the next one. Again, I know we do have a couple of people here. If you have a question, feel free. Okay.
Oh, sorry. Yeah. Can you show us an example for the kinetic energy equation? Can you give us like a practice problem that we can see?
I'm not going to put practice problems on here because then they become like 1,000 slides long. So these slides are short because I don't have practice problems.
Oh, okay.
So I have extra, I can give you extra problems, but you know, sometimes in a textbook you have like 200 slides. That's because they're full of problems. So I would keep the what's new content maybe with a problem here and there, but then all those problems, that's what homework's for.
Okay.
So I'm definitely going to include some of these on the homework for sure. And you have practice problems in your textbook as well already. But
yeah, I'll get to reading them.
Yeah, so I can definitely give you what you want, but in this format, it's kind of not a good location. For now, it's just an equation. There's no numbers associated with it. Here, this is a typical distribution of gas molecules with different speeds. So when we describe gases, we can't possibly look at every single molecule. We just have to look at the average, right? So it's almost like a city population. You don't really want to look at any one person. You want to say on average, everyone's going to be on the freeway between these hours. On average, everyone's going to be at the beach. On average, so we start to look at averages when the population gets very large. So for a gas, the population is huge. We look at averages. But when you look at averages, you have a distribution. Now, this is Maxwell's distribution, and it's got three distinctive locations within the distribution that I want my students to be aware of. The very top of this distribution, here it's labeled UM. This is the modal speed of molecules. So if you take a population of molecules, some of the molecules move slowly, some of the molecules move quickly. The modal speed is the most reproduced speed. It's literally the mode from mathematics. So if you're aware of what the mode, the median, and the mean are, if I gave you 10 values and 2 repeated, that would be the mode. So you rank things from lowest to highest value, and you look if there's any duplications. The more duplications you have, that then suggests that that value that's being duplicated is the mode. And here that becomes our most probable, because if it's duplicated, it's going to increase its probability. So our modal speed is the most probable speed. And that hits the very, very apex of our distribution here. Okay, slightly to the right is the mean average. So this would be if you were to go in and look at every single member, calculate the speed, add them all, divide by the total number. So the regular mean average, that would be the average speed. And that would be this one here. Slightly to the right of that again, so definitely not at the peak anymore, but slightly off center to the right of the peak, is probably the most useful way of thinking about the speed of a gas. It's called the root mean square speed. It has a distinct equation. To be honest, at Chem 65, we're probably not even going to calculate it. I just want you to be aware of it. This is really something you do in general chemistry, and all we have to do in Chem 65 is get you ready for Gen Chem, so it's not a massive shock to you. But again, you know, to go back to Diego's point, the calculations for KMT that he was requesting, to be honest, we probably don't even have to do that in Chem 65. It's more just to raise your awareness to it. The calculations come probably in a different course. Here, again, we're just raising your awareness to it. So that thing that you're going to learn how to calculate eventually, you know what it is, and you're not just calculating something you don't have a feel for. The reason why the root mean square velocity, and in general chemistry, we typically derive this equation. You can derive this from kinetic molecular theory. It's linked to the average temperature. So the reason why it's useful, you can actually derive it from kinetic molecular theory. You produce the others from the derived variable URMS. So anyway, for now, I just want you to be aware that we're looking on the average at speed distributions. There are 3 distinctive speeds that we typically talk about. And the one at the apex is the modal speed. Slightly to the right of that is the average speed. Slightly to the right of that again is the root mean square speed. For now, it would be great if you can just label them, even if you don't know the equation or you can't calculate them. Just to be able to label the 3 speeds on a distribution like this would be probably the Chem 65 goal. Okay, pressure. What is pressure? Because gases have it. Pressure is force per unit area. That's all we need to know about pressure. You can measure pressure in a barometer. So one of the units of pressure that we will become familiar with is millimeters of mercury. So literally, this is millimeters, as in, you know, you measure it with a ruler, millimeters of mercury. And if you were to take a barometer like this, so basically an inverted, long, thin tube, you fill it full of mercury, and then you, I don't know, put your thumb over it, submerge it into a vat of mercury, and then the height of the mercury in the tube that you have inverted would drop. Some of the mercury would spill out, but then it would stop. It would stop at a height of 760 millimeters. And that's because it's being counterbalanced by atmospheric pressure. So you've got pressure pushing on the reservoir of mercury here, trying to push mercury up into the tube. And then you've got the pressure of the weight of mercury trying to push down. So you've got these forces trying to fight each other. And they cancel when the atmosphere is canceled by the weight of a column 760 millimeters tall. So then we have a direct comparison between atmospheric pressure and a height of mercury. So this is an exact definition. A millimeter of mercury is also equivalent to a torricelli or a torr. So we have millimeters of mercury, torr, atmospheric pressure. I would say they're the 3 common units that we want to be familiar with. There are other units that are less common, pounds per square inch. You're probably familiar with if you drive a car. Barometric pressure, or bar, that's almost the same as a torr, but not quite. But definitely these are the 3 big ones that you should probably be familiar with. And we can get those from a barometer. A manometer is related to a barometer, but it's open at one end. So for example, if you have, this would be a manometer here. So let's say you have a reaction vessel here on the left where it says P gas. And let's say you put some chemicals in here that are going to generate a gas. You've got some measuring liquid here, this red liquid. And it's open to the atmosphere here. So the atmospheric pressure in blue is going to be pushing on the liquid. And let's say this has just got atmospheric pressure in here. You've got two forces, the red arrow, the blue arrow. Neither one of them is going to win. So you have the same height of the liquid. Now let's say that you put some chemicals in this flask. They start to generate pressure. That generation of pressure is now going to push down. So now our red arrow becomes dominant and it pushes the liquid up. And so it's now dominating the blue arrow. We can look at the difference in height of the liquid to be proportional to the difference in pressure. So we can relate the difference in height to the pressure. There's an equation that I don't see here, so I can write it over. Again, the equation's not really the relevant part, to be honest, of the discussion. What am I doing? Okay, wait, yes. Okay, so we can have here the pressure is equal to density GH. So here D is density. So we've got some density of our liquid. If you're using water as your liquid, we'd have to take into account the density of the water. If you were using mercury, you'd have to take into account the density of the mercury. Why? Because ultimately you're measuring force, and force we know has mass in it. So the pressure is related to force. The density has a mass in it, so we're basically getting force pressure from using the density. G is the gravitational potential constant of our planet, so it's 9.8 meters per second squared. So long as you're doing the experiment on planet Earth, we can use planet's gravity. And then height is this difference in height here. So this height, this here would be the height h. So anyway, the equations are relevant. You can forget the equation in a minute. But understanding the visual, if I asked you to label the diagram, you know, for example, which is the higher, you know, adjust this diagram on the left to make it look like the pressure in the round flask on the left is greater than atmospheric pressure. What would happen to the liquid? So just qualitatively managing yourself around the graph is more Chem 65. Deriving equations is more Chem 101. So I would like my students to know what a manometer is. And, you know, what's the difference? Maybe I'll ask this as a discussion question on Canvas. What's the difference between a manometer and a barometer? See what people say. Okay, so these are calculations that we would do in Chem 65. So historically, they go top to bottom, but I think the best way to learn them is to go from bottom to top. So pvnrt is the ideal gas equation. We derive it in Gen Chem, we just state it in Chem 65. So we've got a product of pressure and volume. N is moles, R is the ideal gas constant, T is temperature in units of Kelvin. Here's the numerical value of the ideal gas constant here. Now, again, I have a video, I'll post the link, it's on my YouTube channel, where I actually derive this. You don't need to derive it. You're very welcome to watch the video though, if you're interested. But so long as you know this equation, that's more than enough for us in Chem 65. If you solve for R, so just to give you a feel for how you would make these links, if you solve for R in the ideal gas equation, so you've got R is what? PV over NT, right? So I know that R is a constant, that means it doesn't change. And I know, therefore, that the ratio PV over NT won't change. because it's a constant. So I can write this again. Let's say I say this is under conditions 1. Well, under some other conditions, let's call them condition 2. It's still going to be equal to a constant, right? Any one of them can change. P, V, N, and T can all change, but all together they can't change because they equal a constant. Okay, well now I can say that the initial and final conditions equal each other. If they equal a constant, they must equal each other, right? What if I set N1 equal to N2, which is easily done. I just don't allow any moles in or out. What if I set T1 equal to T2? I don't change the temperature. Well, under those conditions, the N1 T1 and the N2 T2 are common factors and they'll cancel. So what I'm left with under those conditions is just P1 V1 is P2 V2. Well, that's Boyle's law. So from the ideal gas equation, I've just derived Boyle's law. P1 V1 is P2 V2. Right? Now, the way they've expressed it here, and I'm sure on the next slide they have this P1 V1. In fact, I can see it on the next slide. They have this P1 V1 idea. But just while we're on this slide, this says that volume is proportional to 1 over pressure. Well, that's exactly what P1 V1 is telling you. There's an inverse proportionality between volume and pressure. That's a product relationship, right? If I were to double P, to maintain the constant, V has to halve. So I scale up P, I have to scale down V. That's an inverse proportionality. That's exactly what this very pretty lilac letters here say. It's inversely proportional to pressure. If I were to put the N1 and the T1 back, and the N2 and the T2 back, let's go for Charles' law. If I were to, let's see, if I were to set P and N constants, so don't change the pressure, don't allow the pressure to change. Don't let anything in or out, so don't let the moles change. Then I can cancel P1 and N1 with P2 and N2, they're just constants. Under those conditions, what I'm left with is Charles' law. I've just got V1 over T1 is V2 over T2. That's Charles' law. V1 over T1 is V2 over T2. Here we say that volume is directly proportional to temperature. Well, that's the relationship of a fraction, right? If I double the numerator, I have to double the denominator also to maintain the constant. So an inverse relationship is the relationship with a product. A direct relationship is the relationship with a fraction. And I get all of this information from one equation. This is really the only thing you have to know. Everything else comes from solving for R and then looking at what you have in the different conditions. So on the next page, we have those derived versions of the ideal gas laws. So here, so we have Boyle's law, which we've just mentioned, P1 V1 is P2 V2. If we keep moles and temperature fixed. Charles' law, we've just seen V1 over T1 is V2 over T2. If we keep moles and pressure fixed, we can have, I think it's actually split because it can't fit here. We have Avogadro's law, V1 over N1 is V2 over N2 if we keep pressure and temperature fixed. Finally, Gay-Lussac's law, P1 over T1 is P2 over T2 if we keep V and N fixed. They all come from the ideal gas equation if you solve for R. So there's really one equation. if we take everything, so this is what we started with, right? I'll put the R back in just for context. So we solved for R and we said PV over NT is R under initial and final conditions. Well, here we've just got a bit of everything, right? We've got a combination of everything. Here, if we set moles equal, historically, they call this the combined gas law, because again, historically, Boyle, Schall, Gay-Lussac, Amantin, and Trenz, they all came up with a law, and it was when they pulled all those laws together, they realized, we can combine these together. We should call this the combined gas law. Again, historically, learning how to do it might not be the best way. Go to the answer and then reverse engineer all the individual laws back out of it would be the better way to do it. So this is a combination of all the laws together. Again, it looks like there's about 6 or 7 laws. There's really not. There's one law, pvnlt, for one gas law. Okay, so they're the gas laws. What? Oh, did I skip one? Let's make sure I didn't skip one. Yeah, I did skip one. Okay, so we have pvnrt. So I'm going to write that here. We've got PV as nRT. Let's cross multiply this a tiny bit. We know from our discussion of moles that moles is mass over molecular weight. So instead of writing N, I can write moles over molecular weight. Oops, somebody's trying to. Someone's trying to get into the canvas room. And yeah, like the system is beeping. Okay, all right, back to it. We know the PV is nRT and we know that N is moles over molecular weight. So let's write that in. Let's write mass over molecular weight, or molar mass. Molecular weight doesn't matter, it means the same thing. Now let's cross multiply volume with molecular weight. So I'm literally just going to exchange the V with the MW. So I can write my V down here. I can write my molecular weight here. Well, now M over V is just density, right? So I end up getting pressure times by molecular weight is density times by RT. And if I solve for density, it means I bring the RT down here. So that's where this equation comes from. So the density of a gas is the pressure of it, the molecular weight of the gas in question divided by RT. So we can solve for the density of an unknown gas just by knowing its pressure and temperature, which is kind of cool. We don't even have to know what the gas is. I just need to know, well, if I know the density, I don't need to know what it is. Obviously, if I know what it is, I can calculate the density. But if I don't know the density, if I know the density, I can solve for the gas and I can measure the density pretty easily. So that's one derivative of the pvnrt equation. We can solve for density, so that's good. Another thing we can do is to solve for molar mass, which was kind of a stepping stone that we had here, where I can just, at this point, I think it's probably obvious, but I'll just make it obvious anyway. So we just cross multiply. Instead of solving for density, we can solve for MW. So we've got the molecular weight of our gas, or the formula mass, whatever you want to call it, is the density RT over the pressure. And if I don't like density, I can just call it mass over volume. So mass over volume is just density, right? So whether you call it mass over volume or density, you multiply it by RT over P. So we can solve for the density of an unknown gas. We can solve for the molecular weight of an unknown gas, all using the power of the ideal gas equation. That's pretty powerful stuff. If you're impressed by power, that should impress you. Okay. Okay, just a couple more here. Gas laws and stoichiometry. So I'm about, just before I realized I had a 3 o'clock meeting with you, I was making the chapters 6, 7, and 8 homework. So I'll be posting those within the next couple of hours for my students. So there will be some of this type of calculation. Okay, so we've started to look at stoichiometry in previous chapters. Stoichiometry is just doing calculations with chemicals, right? So now we're going to piggyback on the new gas interpretations that we have in our ability to quantify gases. We're now going to add that into a familiar skill set that we have of stoichiometry and just blend the two. So here's a quick example. How many milliliters of nitrogen at a given temperature and pressure are required to produce a given mass of a target compound? We're given a nice balanced equation. So 6 moles of sodium solid and 1 mole of nitrogen gas gives 2 moles of sodium nitride solid. All right, so we have a nice balanced equation. And then we're going to reverse engineer this. So we're asked for grams of sodium we're after milliliters of nitrogen. So the plan is to calculate moles and then calculate volume. So I want moles of nitrogen initially. It won't let me undo that now. Sorry, I know. Zoom is very, if you've listened to any of my videos, you know I curse Zoom out all the time. It was designed by people that failed chemistry classes, I think. It has a habit of whenever you see a black annotation, it's there for life. It won't disappear. So let me get rid of it. All right, let's try that. There we go. All right, so I need moles of nitrogen. So I know from the balanced equation, there is 1 mole of nitrogen equal to 2 moles of my sodium nitride, right? So this 1 and 2 comes from that balanced equation. So I want moles of nitrogen, I write moles of nitrogen. I tick moles of nitrogen from the balanced equation, and I link it to sodium nitride with a D from the balanced equation. I then write moles of sodium nitride here, and I cancel it. By definition, a mole of sodium nitride is its weight in grams. So I go to the periodic table, I look at the mass of sodium, I add 3 of them. I look for nitrogen, I add it to the 3 sodium. I get all of this. That's equal to 1 mole. I take my unit grams of sodium nitride and I put it here. And now I can use my input 10 grams. I multiply 10 by 1 by 1 divided by the denominators, and I get a value of 0.060258. I've given it 3 sig figs because my input had 3 sig figs at the very least. And so I keep a track of my 3 sig figs, and I always give an extra 2 when I know I'm going to use the value again in a calculation. So they're my 2 insignificant digits after my dashed line. Now I've got this moles, I'm going to plug it in algebraically to the pvnrt equation that I've solved for V. So the moles I've just calculated are here. Now I've got the ideal gas constant, 0.082057 liter atmosphere per mole Kelvin. I've got my temperature in Kelvin. So remember how to convert Celsius to Kelvin. So if you have forgotten that, to get Kelvin, we take the conversion 1 Kelvin equals 1 Celsius. We multiply that by our input in Celsius, and we add 273.15. Okay, the units Celsius cancel, and we've got Kelvin equals a number of Kelvin. So we've added 273.15 to the 23.6 Celsius to return 296.750 Kelvin. We have to convert our Torricelli to atmospheres because I've got units of atmospheres in my constant. So by definition, an atmosphere is 760 torr. So my torr cancels my conversion here, and my atmosphere cancels here. My volume has to be in liter. Again, I've got to cancel the liter in my unit. So essentially, the units in R tell you the units that you need in everything else. I need liters, atmospheres, and Kelvin. All the units cancel except for the volume units, which are preserved. Here I just convert liters to milliliters again. So my final answer after I plug in the numbers is 1,496.8 milliliters, which we've kept track of our significant figures. We now round to 3 sig figs. The 6 is greater than 5. It adds 1 to the 49. So that 49 becomes 50. But we have to write 150 to 3 significant figures. Well, as written, it's only 2 significant figures, right? So the only way to make that third digit significant is to write it in scientific notation. So 1.50 by 10 to the 3 milliliters is the only way to represent 3 sig figs for that order of magnitude. So that's what I mean by stoichiometry in gas calculations. We're using our regular mole type calculations, but with the addition of, we've now got a new way to calculate moles using pvnlt. Any questions from anyone about that? We only have a couple more slides, so. No, okay, then onwards and upwards. You should know about standard temperature and pressure in a Chem 65 class. Okay, why? Because these variables are temperature sensitive, so we have to know how they're affected by things that vary them. Because the variables we're measuring pressure, temperature, volume, they're all temperature sensitive, we standardize temperature, or we have the language of standardized temperatures. So this is something you'll see common in any natural science like chemistry or physics. You'll have standard values. So STP is standard temperature and pressure. The T is 273.15 Kelvin. That's standard temperature. Standard pressure is 1 atmosphere. So here it says 0 exactly, but you're not going to put 0 in a calculation. You'll just get errors. But then you realize, oh, well, why would I do that anyway? Because I don't use Celsius in calculations, I use Kelvin. So it's exactly equal to 273.15. Because when we have our conversion, remember our conversion, Kelvin is the fact that 1 Kelvin equals 1 degree Celsius. Then you can put your input of 0 Celsius in, and then you add 273.15. Okay, well, this thing just multiplies 0, so that's 0, but then you add 273.15, so the Kelvin is just 273.15. Okay, at exactly STP, 1 mole of any ideal gas is exactly 22.414 liters. It's worthwhile knowing that, because whenever you are told in a question you have STP conditions, you can invoke that equality and use it. So here's an example. How many milliliters of iodine in the gaseous form forms when 15.7 grams of iodine as a solid sublimes. This just means becomes a gas without becoming a liquid. So it goes from a solid to a gas directly under the conditions of standard temperature and pressure. So I don't need to use pvnlt. I can invoke the equivalence of STP, which is this thing here, right? That's something I can invoke under these conditions. So I need volume in milliliter, right? If I need milliliter, I immediately write milliliter. Now my input is liter, so I have to convert milliliter to liter. Okay, well, there's 1,000 milliliter equal to 1 liter. Now I put liter here. Okay, well, now I can use the liter from my STP. By definition, 22.414 liter of any ideal gas is a mole of that gas. I promote mole up here. Well, by definition, a mole of anything is its weight in grams. I go to the periodic table, I look for iodine. I've got 2 of them, add the weight of 2 of them. I get this value. I put grams of iodine up here, and that's my input from the question. Run the numbers. I'm good with 3 sig figs because of my input. I give 2 extra digits as I should because I was raised to be a good chemist. I use the first insignificant digit to round my last significant digit. The 6 adds 1 to the 8 becomes 9. I can't give any more significant digits, so I just use them as a place-saving 0, and I have order of magnitude 1390 milliliters. Yeah, lots of words in chemistry. Lots of words needed to describe what's happening. I think that's why cave people never invented chemistry. They didn't have enough words to describe it. You needed a high integrity language in order to describe it. Okay, the final topic or two, Dalton's law of partial pressure. So this is John Dalton, the same John Dalton as in Dalton's atomic theory or Dalton's law of multiple proportions. Same guy, one of the patriarchs of the discipline. And it basically says something very obvious. The total is the sum of the parts. That's all it says. The total pressure is the sum of the partial pressures. So for example, if I tell you that the room has 1 atmospheric pressure of air, and the air is made up of oxygen, let's say, I don't know, 20% oxygen and nitrogen, let's just for argument's sake say 80%. So 100% air at 1 atmospheric pressure is 20% oxygen, 80% nitrogen. Well, then that must be 0.2 atmosphere plus 0.8 atmosphere, right? 1 atmosphere is now the sum of 0.2 plus 0.8. So it's as straightforward as that. Obviously, this is going to be developed a little bit in Chem 101. So we don't have to worry about that now, but this is the building block that they're going to build upon in your next class. But this is all we need to worry about, to be honest, at this point. We can treat each piece of a gas as a unique entity, like a Lego brick. So if I have a mixture, I can look at one piece of that mixture in isolation. And it all links back to kinetic molecular theory. So at the very start of this little overview of gases, we said the kinetic molecular theory is diffusion. Diffusion is the straight line, random motion of gas molecules. It's the reason why gases take the shape of the container, because on average, they go that way, that way, that way, that way, that way, that way. They go no which way, so they go all ways. And they eventually take the shape of the container because they don't stop moving. We said that they are point particles that don't interact with their neighbor. Well, if they're point particles that don't interact with their neighbor, I can look at them in isolation from the neighbor. And that's all we're doing here. We're fulfilling a promise. We can look at them in isolation because they don't interact with their neighbor. They're not influenced by their peers. Okay. Here we've got it nicely inserted as the pvnlt equation. So here we've got the ideal gas equation. P total is N total over RT over V. Instead of N total, we can write the sum of all the moles. So clearly, like I've got this proportionality here, the proportionality can either apply to the pressure or the moles. Why can I apply it to both? Ah, correct. There's an ideal gas law for that. So remember, the relationship between P and N is, if it's a fraction, is it direct or indirect? If I write this equation and I write P over N as a fraction, this would be a direct relationship, right? Because if I were to scale P by, let's say, a factor of 2, I'd have to scale N by a factor of 2. So the scale could cancel and I'd preserve the equality. So whenever you have a fraction, the numerator and denominator are related directly. So pressure and moles are directly proportional to each other. So I can either have the sum of the total pressure is the partial pressure, or the total moles is the sum of the partial moles. That's what this thing down here is talking about. You have mole fraction, where you have the ratio of the partial moles as a numerator to the total moles as a denominator. And it's equal to the same type of thing where you've replaced moles with pressure. Likewise, with volume, you have this direct proportionality as well. And this thing, it looks like X, it's really a chi. The Greek letter chi, which is really a slopey X. I guess I couldn't find the chi symbol here in the slides. But it's really a chi, Greek letter chi, and it's just a fraction. Okay, so Dalton's law of partial pressure. And then the very last slide, again, I keep these short because nobody reads 200 slides. Some people might read 13, but nobody's going to read them if there's 100 in. Okay, this is just to give you, again, it looks like another example. So an aluminum can is dropped in excess. Muriatic is just a silly word for hydrochloric acid. This is what it's called if you buy it in the store. It's just hydrochloric acid. At a given temperature, a given pressure, and a given volume of gas is produced. Okay, so you've got this balanced equation here. 2 moles of aluminum added to 6 moles of HCl produces 3 moles of hydrogen, and you make 2 moles of aluminum chloride. Okay, you're given some information at a given temperature, what the pressure of the water vapor was. What's the mass of the aluminum can? Okay, so kind of maybe an unnecessarily complicated example, but definitely not something out of the realm of possibility in Chem 65. This thing, the only thing that's probably not anything to worry about, to be honest, is this thing here. So let me explain this real quick. I'm saying not worry about, not that you can't figure it out, but what this says is, okay, when you produce a gas in water, when a gas is produced in a liquid and it bubbles through the liquid, it's going to kick out some of that liquid with it, right? It's going to splash some of that liquid away. So the pressure produced is going to be wet, and we're just going to subtract the moisture from the dry gas. So we have to subtract this partial pressure of water. This is something, if you needed it in an assessment, I'd provide you with these values. This is stuff that you find in a table. So we would measure the total pressure of gas produced. And we'd have to know to subtract the moisture out the gas. Anyway, it's practically not relevant to us right this second. Suffice it to say we have a corrected value. Okay, this is much more something that we should worry about. We've got our ideal gas equation, pvnlt, we solve for n. We can plug some numbers in here. Algebraically is fine. We only have 4 variables. So we have pressure. We know from the R constant, the pressure has to be in atmospheres. So we just initially convert our given millimeters of mercury to atmospheres. So I know that an atmosphere is 760 millimeters of mercury. That's an equality. That allows me to, what does that allow me to do? That allows me to get out of millimeters of mercury and get into units of atmospheres. Sweet. Okay, so now I've got pressure in atmospheres. Now I've got to multiply that by V. So V has to be in liter. Well, I've got milliliters. Okay, well, no big deal. So I need liter, but I need to use my milliliter input. Well, okay, a liter is 1,000 milliliters, and my milliliters will cancel my input milliliters. Okay, sweet. So I've circled what I've kept. I've kept pressure in atmospheres, and I've kept volume in liters. Now my temperature has to be in Kelvin. Here she is. I've added 273.15 to my temperature in Celsius. I've got my temperature in Kelvin. Sweet. There's my Kelvin right there. Now R is 0.082057 liter atmosphere per mole Kelvin. So if I put per mole Kelvin down here, it's a double denominator. So the double denominator wraps up and becomes a numerator. So that's why I have mole Kelvin as a numerator now. It was just a double denominator before. Well, that's cool because that's how my Kelvin's going to cancel, and that's also how my liter is going to cancel. The only unit that won't cancel now is moles. Well, that's convenient because that's what I want. I want moles. So I get a given value of moles that I'm going to use. So I've got my moles for my pvnlt equation. And remember what I'm trying to calculate? I'm trying to calculate the mass of the aluminum. All right, so I need mass of aluminum. So I know that the mass of aluminum is its weight in grams. So I look at the periodic table. I've got the mass of aluminum in grams, and I set that equal to a mole of aluminum. Well, a mole of aluminum, I write it here from the balanced equation. There's 2 moles of aluminum equal to 3 moles of gas. So there's my 2 to 3 mole ratio. I can now use my input moles of gas from the previous setup. And then the last thing is just to give you the units that were requested in the question. I want to give units in milligrams, not grams. So I just use the metric conversion to get back to milligram again, and I get my final answer in milligrams. Okay, so that's all the slides. I tried to keep it as short as possible so that people actually take a few minutes to watch it. For the benefit of the recording, I'll close it now, and then I'll see if any students have any questions. Stop recording.